my screen again. Okay, this one. And what I want to bring forward for you is this equation again. So last time when we were discussing, we looked at this very simple equation associated with 50% additional air with methane as a gas reacting with air 50% more than what we need in order to generate CO2, some water, some oxygen, extra oxygen because we have the extra 50%, and then the nitrogen passes through. And so, as we just stated, in order to solve a problem like this, each of the individual components has a heat of formation, and depending on what temperature they're at, they have then additional enthalpy and additional delta H. And so when we're dealing with the carbon dioxide or the water or the oxygen or the nitrogen, depending on what the temperatures of the products are, we have to use that equation or that table 23 in order to get the delta H that we then add to the heat of formation. And so in the next video, you're going to see us talking about this a little bit further and introducing what is referred to as the adiabatic flame temperature or the heats of combustion. And so the differences between the adiabatic flame temperature and the heat of combustion is when we talk about the adiabatic flame temperature, if I came in with these components and as they transition to these components, if no heat was lost from the combustion chamber and all the heat stayed in, what would happen is that heat would then cause all of these components to raise in temperature. And so a first law balance would then say that these components will rise to a temperature, an adiabatic flame temperature, such that the products in the enthalpy equals the reactants enthalpy. And so we're going to perform this calculation. Now, the other term that is going to be discussed on Thursday is what's called the combustion heat. And so combustion heat is if you came in with the left-hand side here and you allowed the right-hand side to come out at 25 C or 77 Fahrenheit. The question is how much heat has to be released in order for the products to come out at that lower temperature. And that then is referred to as the combustion heat of the individual fuel. Now, typically the combustion heat is written for a stoichiometric component. And so one would take out the 1.5 and just have the 2 times these. You would not have this term here, the oxygen, and you would have a smaller amount of nitrogen. Okay, so what we're going to do is we're going to go back to our test software and we're going to make up 2 mixtures, well, actually 3 mixtures like we've done before. The first mixture is going to be our methane, our fuel. We'll call that mixture A. We'll have our second mixture, which is our oxidizer. That will be mixture B. And then we'll bring them together and form a mixture C, which is going to be the products. And what we'll do is we'll specify what the temperature of mixture A is, what the temperature and pressure of mixture B, and then we'll set the pressure of the mixture C to be 1 atmosphere, and we'll allow the first law to calculate what the temperature must be if there is no heat transfer. And that would then be the temperature that we would refer to as the adiabatic flame temperature. And so we're going to do this with the tools in tests that we already know how to use, and then we will then look further on Thursday at some of the other applications that are in test. And so I now have in front of you, you now see that we have, I have the test software, and you should be seeing that. The application then we're going to perform, we're going to have a flowing system mixing process. And so it's going to be a mixing multi-flow system. So I'm going to select this right here, and we're going to allow the mixtures to be a group of ideal gases. And so we're going to select this this particular substance. And as you can see, you can kind of see a little picture here. We have inlet 1, inlet 2. One's going to be mixture A, that's the fuel. One is mixture B, which is going to be the oxygen and nitrogen. They mix together, possible heat transfer away, and then they hit the exit, which will be mixture 3. The difficulty of using this software to solve these problems is that we have to make sure that we put in the right proportions of everything. Now, when we go back, you'll notice here that there is a combustion test app. And when we get to that, you'll see that we can very easily select fuels, select air, and have it do all the calculations of the theoretical combustion. And so we're going to do it in the mixing multi-flow for right now. Okay, so similar to what we had before in one of the homework problems where we had a couple of tanks, we're going to specify that mixture A is our 1 mole of methane. So we slide down here and we find, let's go ahead and we're going to put it in as 1 kilomole of methane, and I'm going to add it. And so basically this is mixture A is just fully equal to methane. I'm now going to specify a mixture B, and mixture B will be in kilomoles. And mixture B now is going to be the amount of the 2 substances. And so we know that it's going to be, for oxygen in kilomoles, it's going to be equal to 3 kilomoles. Oops. Because it was 1.5 plus a 2 times 2. And so this is our oxygen. And then we also know that the nitrogen is equal to that same 3 times 3.76. And so that is the amount of nitrogen. And so now we've made up our mixture that corresponds to the oxidizer as mixture B. And now we're going to go to mixture C. Now mixture C, we've already balanced the reaction in the picture that we showed before, and we know that in mixture C we have 1 carbon dioxide. Let's again switch over to kilomoles. We have 1 carbon dioxide. We have 2 waters, and we have 1 oxygen. And then we have 1128 nitrogens. And so I'm going to go ahead and I'm going to put that in as, excuse me, as equal to 3 times 3.76. And so we see that's 11.28. So now we have our mixture C. Okay, so the next step, as we saw before, was to go into our state panel and say what we know about mixture A. Now you'll notice that it defaults, and when you see this yes here, it says formation enthalpy yes. And so what this is doing is it's adding or making sure that the formation heat is included in the calculation of the enthalpy for mixture A, which is the methane. And so we're going to go ahead and just put everything in at one atmosphere of pressure. Pressure won't have a strong influence in combustion until we get to chapter 14. And we're going to go ahead and say that our temperature is coming in at 25 C. Okay, so here's our temperature and pressure for mixture A. And what you'll see then is this is the mixture associated with the methane. Okay, so since we need to take this mixture A and add mixture B to it to form mixture C, we have to say how much of this are we bringing in? And so since we have 1 mole of methane, okay, now when we write these equations, we write them in terms of 1 mole, but as long as we're consistent and just have the right mole percentages. And so for this particular problem, I'm going to say that for the methane coming in, I'm going to say 1 mole, 1 kilomole, corresponds to 1 cubic meter per second. So I have a flow rate, okay? And again, because it's a gas and because volume and moles at a given pressure are related to each other, we're going to basically say then that we're bringing in 1 cubic meter per second, or this amount of mass flow rate of the methane for mixture A. Okay, so what is state 2? State 2 is mixture B. And mixture B is also at pressure 1. That is the 1 atmosphere. And we're going to allow the temperature to be temperature 1. So same temperature, same pressure. Doesn't have to be, but in this case, we're going to say the air is at the same temperature as the gaseous methane. And now we need to put in proportionally, excuse me, the amount of volume of the air. And in this particular case, we know that it's going to be equal to, now I'm going to, the 1.5 times 2 is 3, and then times the 4.76. And so what this is the total number of moles that correspond to the air. Since it's 1 mole of oxygen and 3.76 moles of nitrogen times 2 times 1.5. And so that's where I get this number. And upon doing that, I then see that the MDOT is 16.83. If I compare that to the MDOT of the fuel, if I took the ratio, I would then get the fuel to air or the air to fuel on a mass basis. Okay. If I did it with the volumes, I would get it on a volume basis. And so now I've put together my mixture A, or I have my mixture A and my mixture B in a consistent set of masses coming in. And now I'm going to specify what state 3 is. That's the final state, which is mixture C. Now, what do I know about mixture C? I'm going to allow mixture C to have the pressure of 1. I'm going to allow it to calculate the temperature T3 based on the device panel, an adiabatic device panel. And so what now can I say about this mixture? Well, I can come over here and I can say that m dot 1 plus m dot 2. I know that the two masses have to add up to be the third mass. Okay, so I have that information I can put in. So I'm now going to go over to the device panel. Okay, nothing got calculated because it doesn't have enough information to calculate the temperature until I tell it what's gonna happen. And so this is a multi-mixing device, open and steady, coming in with mixture A, coming in with mixture B. Those are the two. Coming out with mixture C and nothing out of the second port. No work being done. And here's where, because I want to calculate the adiabatic flame temperature, this is where I then can put in a Q dot equal to 0. And so now this is my first law of thermodynamics, and it should be able to now calculate what is the exit temperature of state 3. So I do a super calculate, I go to the state panel, and I see now that the answer is 1790 Kelvin. And so that is the temperature that is required for the products to have the same total enthalpy as the reactants. Okay, now to prove that, I'm going to go to my I/O panel, and I'm going to calculate an H reactance. And I'm going to say H reactance is m dot 1, which is mixture A, times the enthalpy of mixture A, which is H1. Okay, that's in kilojoules per kilogram times the mass flow rate, and then plus m dot 2 times mH2. Okay, so upon doing that, I have a kilogram per second times a kilojoule per kilogram, and I have now, this would then be in kilojoules per time. And that's my enthalpy of the reactants. I'm now going to go up here and I'm going to calculate the same thing for the products. Okay, so oops, prod. So my enthalpy for the products is equal to the m dot 3, which we know is the combination of m dot 1 and m dot 2, times the enthalpy, which was determined associated with the temperature that it determined iteratively as being 1700. And so now I see that it calculated the H products, and those two are equal to each other. And so when the software, upon looking at the device panel and recognizing that the heat transfer was 0 with no work, it had to come back and it had to iterate on this value right here until, as you can see, the J3, which is related to the enthalpy and the m dot, okay, became a certain number. And so that's how it calculated that value. Now, if I wanted to, okay, I could change the game. And I could say, well, let's go back to the device panel. And this time I'm going to turn off the adiabatic nature. And so I'm going to say that Q dot is to be calculated. And that is going to be calculated based on what I assign for this value here. Okay, so what I did was I had set this equal to unknown, and I went to the state panel and I had to super calculate in order for me to be able to put a number in here. And so let's say that we guessed that the temperature was 1000 Kelvin. And if I guessed 1000 and I did a super calculate, I go back to the device panel, I see that the Q dot is not 0. And so I would say, well, my temperature here must have to be a little bit higher. Okay, and so I would write this down for 1,000. And then I would come back to the state panel and I'd say, okay, well, let's see what it is if it's 2,000. And so at 2,000, I'd go to the tables and I'd calculate all the values. I do a super calculate, and I see that it's now a positive number. And so I guessed 1,000. I then guessed 2,000. And in both of those times, I went to my tables and I got the enthalpy of state 3. In one case, the energy balance was negative. In the other case, the entropy, the balance was equal to a positive. And so I recognized that I would have to iterate back and forth. And so in the old days, I hate to say that term, but in the old days, when you were using a set of tables, you had to put in a table value. You had to then do all the calculations, and then you would go to see if you're closing in on this value being equal to 0. Okay. Fortunately, the software is such that you can leave this off. You can go back to the device panel. You can set the Q equal to 0, and you can do a super calculate, and you can find, oops, it should have. Okay, hold on. I don't think, okay, it did not take that value for me. Okay, now let's try it. And we look at state panel. Okay, so the answer is 1790. And so what we did using this mixing test app is that we assigned ourselves a fuel as mixture A. We gave it a temperature. We assigned the oxidizer, and we gave it a temperature. We also specified how much oxidizer there was with respect to the amount of fuel. And so this was an important step here to get the right stoichiometric with the right excess air term. Okay, so, and then we said, okay, here is our state 3, and we had to make it up as mixture C. We had to perform the stoichiometric balances. And then once we did that, we were able to either assign the temperature. If I'd gone back here, and if I were to turn off this heat here, and if I go back here and I would set this temperature, super calculate, set this temperature to equal to T1. Okay, so this would be the products come out at the same temperature as the fuel and the oxidizer went in. And if I do a super calculate, then I get a number here. And what that number is the combustion heat. And again, that was a number that if you went back to that table I showed you, corresponded to how much heat has to be taken out of the combustion chamber in order for there not to be any temperature rise in the output. Okay, so any questions about this? It's really slick how this software, again, can do what used to be quite laborious in terms of coming up with an adiabatic flame temperature calculation. As I said, next time we'll investigate the actual test app associated with combustion. And in the combustion, what we just did was a non-premix combustion. We brought in the fuel, we brought in the oxidizer, and we formed products. And so what you'll see is something that looks similar, but now you'll notice that we can specify, instead of saying mixture A is the fuel, mixture B is the oxidizer, mixture C is the products, they've defined it in this particular fashion. They allow you to put in the fuel, and in our case, the fuel was methane, 1 mole of methane. So that's our fuel. And then when you ask for the oxidizer, we put in dry air, and so we just added it. And then what we now can do, once we have calculated put in the oxidizer as air, we can go to this select an action. And what this allows us to do is we can say, balance those two as a theoretical combustion. And then we execute. And what happens then, it actually balanced the stoichiometric equation. Now, had I said balance with a known excess of air, I could do this, and I could put in right here 150. Okay, and I could say execute. And upon doing that, now it determined the balance reaction that we just looked at. It's methane plus a little 50% more oxygen along with its corresponding nitrogen. And then here is our equation. And then we could go to our, our products, and we see these are our products, and they've already put them in. This is mixture C. And so we've got all of that. And then we can go to the device panel, and we can basically say that our device, fraction, state panel. Oh, we have to give our states. And so state 1 would be, in this particular case, it'd be 1 atmosphere of pressure. That was our fuel. And at a temperature of 25. And see, now you don't have to worry about putting in the vol dot and the m dot. It normalizes it to 1 mole of methane. And then our state 2, which is our oxidizer, is going to also be the same pressure, and it's going to be the same temperature, T1. Again, it already figured out the m dot based on the formulas. And then state 3 is our product, and it's coming out at 1 atmosphere. And so now again, in this case right now, we now want to go back to the device panel. We're going to come in with state 1, which is the fuel, state 2, which is the oxidizer, and state 3, which is the products, with no heat transfer and no works. And now do a super calculate, go back then to the state panel, and there's the same number that we got before. And so, as you can see, and I guess I decided to go ahead and do it because we had some time remaining. We did this same problem in 2 different ways. One where we just put together our own mixtures, and then the second one which was adapted for combustion specifically, which really allows you to put everything in, put in the percentages of theoretical excess air, and again, set up all the conditions and go for that. So with that, I think that's all we really need to say for today. I'm going to call the meeting to a close. If anybody wants to stay on to talk about optimization or anything else like that, we still have 5 or 10 minutes. And so with that, we'll see everybody on Thursday.